Okay. Thanks for the organizer. So, hello everyone. I'm Zhenjun Zhao, a postdoc at the University of Zaragoza, working with Javier Silva. So today I will talk about my recent works, which is trustworthy geometry, perception, certifiable optimization, and robust estimation. And this talk will be divided into three parts. So first, motivations, and second, three recent works of mine, and finally, some open challenges in global optimization. So first, motivation. So why we need trustworthy geometry perception? Traditionally, geometry problems are often formulated as non-linear optimization problems and solved using local methods such as Gaussian-Newton and some existing local solvers. However, the highly non-linear and non-convex nature of both objectives and constraints makes local methods sensitive to initialization and fails silently. Furthermore, no optimality guarantee. So we need certifiable optimization. We need globally optimal and certifiable solutions. We should know when it is correct. And two research directions in my research in the trustworthy geometry perception. Certifiable global optimization, convex relaxation, and polynomial methods providing formal optimality guarantees, and which is also our recent ICRA workshop paper, and robust estimation perception reliably under motion blur, dynamic scenes, and featureless environments. For robust estimation, you can scan the QR code for more details, and I will focus the first direction in this talk. So that's the first part. Then let's move to the second part of this talk. I will introduce three works in the certifiable global optimization. First, GlobustVP, convex relaxation for robust vanishing point estimation in Manhattan world. In a 2D image, lines that are parallel in 3D space appear to converge at a single point known as the vanishing point. A space containing three orthogonal sets of the parallel lines is referred to as a Manhattan world. Vanishing point is a fundamental concept in 3D vision with broad applications such as structure from motion, simultaneous localization and mapping, camera rotation estimation, and structural understanding. In this work, we address the problem of joint vanishing point estimation and line label from a single image given a set of unlabeled line segments and the camera's intrinsic parameters. Our goal is twofold. First, to correctly assign each line segment to its corresponding vanishing point or to an outlier class. Second, to estimate the locations of each vanishing point. In this paper, we evaluate each method according to the following criteria. Global optimality. The solution must be global optimal. Efficiency. It must be practical. Outlier robustness. It should handle outliers reliably. Generalization. It must work across diverse data sets. There are three lines to address this problem: ransack-based, branch and bound, learning-based. However, they cannot simultaneously achieve all criteria described above. Our method, GlobustVP, is designed to overcome the trade-offs this in previous approaches. It's built on three insights: problem reformulation, convex relaxation, and iterative acceleration. Through these three insights, our method satisfies all four criteria introduced before. Let's begin with the first insight. Given the problem of joint vanishing points estimation and line labeling, we find the core difficulty lies in how to represent the discrete labels. Our core idea is to introduce two continuous constraints. The first are quadratic constraints enforce every label to the either 0 or 1. The second, a linear constraint ensures each line to be associated with only one vanishing point or the outlier class. Given all lines, we can collect all the labels into a permutation matrix. Consequently, we can get the corresponding matrix-wise constraints. The overall primal problem formulation includes three key components. First, the objective function, as we just discussed. Second, the matrix-wise constraints on permutation matrix. Third, the Manhattan constraints on the vanishing points, which enforce their mutual orthogonality. With such insight, we can successfully reformulate the hard assignment problem into a continuous constraint optimization problem. As a preliminary step for insight 2, we lift the variables of the primal problem into a higher dimensional space. This leads to an equivalent formulation, quadratically constrained quadratic program. However, this QCQP is non-convex. As shown here, non-convex problems often contain multiple local minimums. To overcome such non-convexity, we apply a powerful technique, which can relax the QCQP to a convex problem. First, we construct the Lagrange dual of the QCQP, which gives us a convex dual problem. Then we take the dual of that dual problem, arriving at the final dual formulation. This transformation is known as convex relaxation, and the resulting dual formulation is actually a convex semidefinite program, or SDP. This SDP can be solved globally using any off-the-shelf solvers. A critical property is that if the relaxation is tight, the solution of the SDP is exactly equivalent to that of the original NP-hard QCQP. Through convex relaxation, our method not only guarantees global optimality, but can also handle a large proportion of the outlier. Although the SDP formulation guarantees global optimality, solving it with all lines and all vanishing points simultaneously can be computationally expensive, especially in large scenes. Our third insight addresses this challenge through our iterative acceleration strategy. Instead of solving one large SDP, we estimate vanishing points one by one. In the first iteration, we estimate vanishing point 1, treating all other lines are outliers. In the second iteration, we remove lines assigned to vanishing point 1 and estimate vanishing point 2. Finally, in the third iteration, we follow the same procedure to obtain vanishing point 3. Our method, GlobustVP, is designed to overcome the trade-offs in the previous approach. It is built on 3 insights. That's the 3 insights. We also compare our methods with we compare our methods with the BNB and RANSAC under different levels of outliers in terms of accuracy. Our method consistently outperforms both of them. It even maintains high F1 score under 70% outliers. In the terms of efficiency, as shown in the runtime comparison under 20% outliers, our method is comparable to RANSAC and significantly faster than BNB. We evaluate GlobustVP in the real-world datasets. As shown here, in both subway and building scenes, our method achieves a perfect F1 score and minimal consistency errors, significantly outperforming RANSAC and BNB. We also compare with learning-based approach such as neural VPs and PASEC. On the YOD and SU3 datasets, our method outperforms both approaches on YOD and achieves comparable performance on SU3. This difference highlights a common limitation of learning-based methods. While they perform well on datasets similar to their training data, such as SU3, they often struggle to generalize to more diverse or unseen datasets like YOD. Second work, NPC neural predictor character solving homotopy problems with reinforcement learning. The homotopy paradigm is a highly versatile problem-solving framework, widely applied in tasks such as robust optimization, global optimization, polynomial root finding, and sample. Although the specific details vary, their core algorithm architectures are remarkably similar. Specifically, a homotopy problem consists of outer and inner layers. The outer layer is the constructed homotopy interpolation from a simple source problem to a complex target problem. The inner layer is the implicit solution trajectory that we actually need to check. The focus of our work is not on realizing the homotopy process itself, but rather on how to advance along this implicit trajectory more efficiently and speedily. Traditionally, the predictor corrector method is the standard algorithm for tracking such trajectories. Its workflow is intuitive. The predictor first takes a step forward to estimate an initial value, and the corrector then iteratively refines this prediction back onto the true solution trajectory. However, many key strategies in this process, such as what step size and the predictor should take and when the corrector should stop, rely heavily on human experience. These heuristic rules are often inflexible and far from optimal. To address this issue, we propose the neural predictor corrector, or NPC. As you can see on the left, the classical predictor corrector relies on fixed manual heuristics for its step size and correction tolerance. In constraint, our methods on the right replace these manual heuristics with neural networks. Compared to the classical approach, the neural predictor corrector can automatically discover the optimal control policy at each step. To achieve this, we formulate the entire character process as a sequential decision-making problem and utilize reinforcement learning to learn the control policy. And at each homotopy stage, the model observes the current state from the environment, including the homotopy progress, statistics from the previous correction step, and the convergence velocity. Based on this state, it outputs the next action, the step size for the predictor, and the correction tolerance for the corrector. Finally, our desired reward balances accuracy and computational efficiency, guiding the model to find the optimal trade-off. To validate the university of the NPC, we conducted experiments on 4 typical classes of homotopy problems: robust optimization, global optimization, polynomial root finding, and sampling. It is worth emphasize that we adopted an amortized training mechanism with just a single offline training session on the training set, and the model can directly achieve zero-shot generalization on unseen test sequences. These 4 tasks are: first, robust optimization based on GNC, which smoothly transitions from a smoothed objective back to the original non-convex objective, that is, to outliers. Second, global optimization based on Gaussian homotopy, which uh, simplifies the objective landscape through Gaussian smoothing and then tracks back to the global optimal. Third, polynomial root finding based on homotopy continuation, which continually tracks the root trajectory from an unknown simple equation to the target equation. Fourth, sampling based on annuled lagging dynamics. NPC can learn how to efficiently advance three intermediate distributions, providing that our method can also similarly extend to sampling scenarios. Next, let's look at the experimental results. In the point cloud resolution and multi-view triangulation tasks, MPC reduced the total number of iterations and run time while maintaining or even lowering the final error. This proves that MPC has indeed learned on more reasonable scheduling strategy, avoiding meaningless computational overhead. The same advantages have been verified in the other tasks. In the other tasks, the number of the iterations in global optimization is significantly reduced. In the polynomial root finding tasks, MPC maintains a 100% success rate with total time consumption lower than classical methods. In the sampling task, MPC reduces the computational cost while ensuring that sample quality metrics such as KSD remain close to those of classical methods. The final work, a survey, advanced in global solvers for 3D vision. We formulate we survey. This is the overview of this survey, and we divide three parts of the survey. The first is the global solvers, and the second is analysts, and the third is the applications. We categorize global solvers into three main families based on their underlying principles: branch and bound, convex relaxation, and graduated non-convexity. We provide a comparison of the global solvers, examining trade-offs in optimal guarantees, computational complexity and scalability, outlier robustness, and practical deployment considerations across different methods, families and method families and problem scales. We survey how global solvers have been applied across classical 3D vision problems, including Wahaba problem, vanishing point estimation, absolute and relative post estimation, 3D registration, rotation and translation averaging, triangulation, post graph optimization, and boundary adjustment, highlighting algorithms typical performance trade-offs and open gaps. That's the second part. So final section, open challenges. Three open challenges are highlighted. First, scalability. The global optimality guarantees provided by branch and bound and convex relaxation methods come at significant computational cost, with complexity growing for large-scale problems. Addressing this scalability bottleneck while previously certifiable remains a central challenge. Second, how to combine deep learning with global optimization. Foundation models produce impressive predictions without certificates, but impressive not equal to certifiable global optimal. So this is indeed a direction to study and research. Third, evaluation. The field lacks benchmarks and evaluation protocols for comparing global solvers across different problem domains and scales, hindering progress and fair comparison of the method. So thanks for my amazing collaborators. Thanks. Any questions?